I'll make a short video here relating time reversal operator in accordance with Newton's principles of classical mechanics, and not conjugate to the principles of entropy as demonstrated by Boltzmann and others. This will be purely mechanical in its exposition. First we will consider a point particle and we will designate its position at different times. X be the variable, the position, and the position be A, B, C, D, E, and F. Okay, then we'll get the times. That is 0 time. This is given by del t, or you may write t. I write del t here. This is 2 del t. This is 3 del t. This is 4 del t, and this is 5 del t. Okay, now what we see is this, that now we're going to calculate the average velocity between two intervals. Now we will consider the interval between A and B. Then this interval, the average velocity is given by the distance traveled. What is the displacement? B minus A. And what is the time interval? Del t. Distance by time gives the velocity. Here we will calculate the average velocity. We will go to infinitesimals by replacing del t by dt, tending del t to 0. Now between B and C, we can write C minus B by del t, and so on. Say D minus C by del t. Del t is the difference between the time intervals. D and D, D minus E by del t, and E and F, F minus C this will be E minus D. F minus E by del t. Now it will be our apprehension to calculate the average acceleration between two events. The average acceleration is the rate of change of average velocity. So between these two events, rate of change of average velocity is C minus B minus A by del t square. Then this gives us C plus A by del t square. Okay, now similarly between these two intervals, it will be D plus B. This D minus C minus B by del t square. Between these two intervals, it will be D sorry, it will be E plus C by del T square, and last it will be F minus plus D by del T square. We are over and out with the first calculation, first part of calculation. You must see this. This is how it goes. I'm going to take a screenshot here. Now we'll repeat it, but in a innovative way, in a new way, which may seem enigmatic at the first approach, but it will be very easy as you learn it. It's not totally intuitive, because what we are going to do is reverse the time, but time flow doesn't reverse. We know that time flows in only one direction, and this is called the arrow of time. So how can we reverse the time? So one class of thoughts, school of thought, proposes that time can be reversed if the events associated with time are reversed. So how can we reverse the events associated with time? We can consider these A, B, C, D, E, F, G as different instances, screenshots of a cinema. Then we can run the cinema backwards, just from F to A. Then we can say that time is flowing backwards. So this is a kind of thinking, but not totally approved by scientific minds, that if we reverse the stages of the cinema, we are actually playing the cinema with time going in the backward direction. So if we take that view, then we have the same thing. We'll write it over here, but it will start with F and then E and then D and C and B and then A. This will complete our positions, and the time intervals remaining the same. The time intervals would remain the same because this is intuitive for between two events, whether you run it backwards or you run it forward. It is reasonable to say that it takes equal amount of time between two intervals. So this will be 0, and here we have del t, here we have 2 del t, here we have 3 del t, here 4 del t, and 5 del t. Okay, time is running in backward direction, or what we are doing, we are running the stages of the cinema backwards with time running in the forward direction. See, time runs from here to here. The arrow of time remains the same. What we are doing, we are cleverly seeking an analogy to the phenomenon. So what will be the average velocity? We are calculating the average velocity. Then from 0 to del t, it will be E minus F by del t. See here, it was F minus E by del t. over here, over here. Now it is just the opposite. The velocity reverses its sign, e minus f by del t. And here it will be d minus e by del t. Here it will be c minus d by del t. Here it will be b minus c by del t, and here it will be, have you seen it? I think it has some problems due to tremors in my hand. C a minus b by del t. Okay, we are finished here. We see that the same velocity appears here and here, but with opposite signs. For example, the a minus b by del t was the last one. Here is the front one, the first one is b minus a by del t. Just the reverse. Now we calculate the last part, but not the least, the average acceleration. So how do we come to it? See, the average acceleration is the rate of change of average velocity over the interval. So rate of change of average velocity is d minus f minus e minus f by del t square. Then it becomes d plus f plus del t square, and low, see, the acceleration that we have got here is equal to the acceleration that we have got there. They are the same. If you compare this, you will also come to the same idea that this minus this by del t square is becomes c plus e by del t square. And here, if you subtract this from this, this gives you have you seen this? I do not have another option, otherwise I would have maintained it in a stand. B plus D by del t square, and here it will be a plus c plus by del t square. Is it not? See, look at it intently. The average acceleration that was over here, then the average acceleration when time is reversed as we have proposed are the same, only they come at different times. So now if we convert this a small time del t to infinitesimals, the thing will be essentially the same. And then the average acceleration will remain the same. Whatever the average acceleration will remain the same, whatever the time intervals be, whatever the velocities be, the average acceleration will remain the same. So so we see here it was at f that we have calculated the average acceleration to be d plus f by del t square, and here at f we have d plus f by del t square. See here, if you compare x and the acceleration, average acceleration, here x and the average acceleration converted into acceleration, this will show that for both the system, if time runs forwards or time runs backwards, you just cannot, by knowing only the acceleration, you just cannot discern that either we are going forward in time or we are going backward in time. And this is the principle that I wanted to illustrate. And so as we know, Newton's equation gives force equals to mass times acceleration, isn't it? This acceleration is the infinitesimal version of average acceleration. Now the average acceleration is constant in both the cases, then the force will be constant in both the cases, and the equations of motion will be the same in both the cases. Hence we cannot only by knowing the mechanical aspects of a system, we cannot discern we are going forward in time or backward in time, whether we are going to future or we are going towards past. So Newton's law is a reversible law. That means it is correct going from present to future and correct from going from present to past. You can't just, without having other innate senses such as those of entropy and other things, or things which you are familiar with, you cannot discern either we are going to past or we are going to future. For example, the best example that we can give is that we may consider a herd of cattle that are spreading, going towards lush fields in pastoral lands. They are going in a particular direction, and they are spreading out from a particular source, you must say. The same thing, if we see it backwards, we'll see that they are not spreading from a source, rather all of them are congregating towards a common place. So we cannot discern which is the right future, right near future of our mechanical system. This property of reversibility is one of the finest of Newtonian mechanics and is seen in other areas of science as well. That is all for the day. Bye bye.